Jai Hind everyone. I, Suvarna Mujumdar, Assistant Professor in Electronics and Communication Department of Ajay Kumar Garg Engineering College, welcomes you on a lecture on classification of 8085 instructions. This is the third lecture on this topic, that is classification of 8085 instruction. Before this lecture, we have covered three types of instruction set. Data transfer, arithmetic, and logical. And in earlier lecture also we have discussed about different ways of classification of instruction on the basis of the memory required to store that instruction. That is type 1 instruction, that it requires only 1 byte to store. Type 2 where it requires 2 byte two memory location to store that particular instruction, and 3 byte instruction where we require 3 memory location to store that particular instruction. Now in this particular lecture or the last two lectures, we have discussed about the instructions which are classified depending on the operation that is performed by that particular instruction. For example, move or we can say MVI, these are the two instructions which are used to copy the data or data transfer operations. So it comes under category of data transfer operations. Move A comma B. This is 1 byte instruction. MVI A comma 34H. This is 2 byte instruction. So on the basis of number of memory location required, these three instructions are 1 byte, 2 byte and 3 byte instruction, but all of them come under a category of data transfer operation. And last lecture we have discussed about arithmetic operation like add B, ADI 34 or 38H, or we had discussed about DAD, D, and many more. We have discussed about sub, increment, INR, DCR. We have discussed about all these arithmetic and arithmetic operation. In logical operation, we have discussed about AND, OR, XOR. Here we can have B, C, D. We have discussed about compare. So these all are the different instructions that we have covered in last lectures. Now in this particular lecture, I am going to cover about the remaining two part, that is branch instruction and machine control instruction. So branch instruction are those instructions which allow microprocessor to change a sequence of program either conditionally or under certain test condition. For example, we have given some task to microprocessor, task A. When microprocessor is performing this task A, and in between with some condition or without any condition to be satisfied, that is conditionally or under some unconditionally, we want that task B has to be executed. And after execution of task B, microprocessor has to return to the main task A. So there are different groups, that is jump instruction, call and return instruction, and restart instruction. There are three groups which come under this category of branch instruction. We will see one by one. In case of jump instruction, there are two types of jump. One is unconditional jump and conditional jump. JMP, this mnemonics is used for unconditional jump, like JMP 20A4. Suppose this instruction is written at 3000 location in a program. So next instruction will be 3012, third location. It is written as move A comma B. So in this way this program is written. So when this 3000 is stored in program counter. Okay. So when program counter is pointing to 3000, this jump instruction will be fetched and decoded and executed by microprocessor. So when this jump instruction is fetched, the opcode will give instruction to microprocessor that now PC will not point to 3003. it has to change the content of PC by 20A4, because microprocessor, when opcode is decoded, this opcode is decoded, and then microprocessor comes to know that whatever the next two location, the data from next two location, that is 3001 and 3002. 3001 it will get A4, and 3002 it will get 20. So this data is then stored in program counter, and now program counter will pointing to 20A4 location, and whatever the instruction written at 20A4 location will be executed by microprocessor. This is unconditional jump. Next type of jump instruction is conditional jump. In case of conditional jump, the microprocessor has to check the condition in a flag register, or you can say the PSW, that is program status word. So, in case of 8085, we have a carry flag, zero flag, parity flag, auxiliary carry flag and sign flag. We have 5 flag registers. So, according to their condition, whether the carry flag is set or carry flag is 0. So, we have two types of conditional jump if carry. It means whenever the carry flag is 1, then only it is satisfied and the control will jump, that is the content of program counter get modified with the address specified, like 20A4 or 3000, whatever the address is specified. In case of jump if not carry, means carry flag is 0, then only it will jump. For example, this instruction JZ20A4, this instruction is written at location, again I am taking it as 3200, okay, and at 3203 location, next instruction is move C, A. Okay. So, when this instruction is decoded, JZ, microprocessor go and check for 0 flag. If 0 flag is set, then the content of program counter gets shifted to 20A4 location. Whatever may be written at 20A4. For example, here it is written as move D, A, something like this, and whatever the instruction is written at this location. Okay. But if 0 flag is not set, 0 flag is 0, then in this condition is not satisfied, it is false. Then in that case, microprocessor, or you can say program counter, will come to the next subsequent instruction, and this instruction will be executed. So, if Z0 flag is 1, then it will jump to 20A4 location and execute this instruction and whatever the next instructions are there, and till the stop of the program or end of the program is written. Otherwise, it will follow the main program. Okay. In place of JZ, if I have written J and Z, then the condition is reverse. Microprocessor will jump to 204A location when 0 flag is 0, Z equals to 0, and it will not jump to this location when Z is equals to 1. So, it depends on the programmer only. So, which condition has to be used for transferring the control. Next is call. In case of call, if we have to call a particular set of instruction in our main program, then we use, like if we have to call subroutines, like in case of if we have to perform some Fibonacci series, or we have to perform some multiple additions, or we have to perform multiple multiplication, one task if we have to repeat it, then in that case we write a subroutine for that program and we will call that subroutine. So, in case of when we have to call some subroutine, we use this call instruction. We have to specify the address where we have written our subroutine. In case of call, the program counter or the sequence of execution gets shifted to a new location, and in that particular new location a subroutine is written, and at the end of that subroutine we have to write another instruction, that is RET. I will next slide we will see what is that RET. But in each subroutine we have to end that subroutine, indicating that microprocessor has to go back to main program. Okay. So, for example, in our main task, our main program, we have written some instruction, and at some location we have called this call 20A4. So, till this PC is pointing, program counter is pointing to this main program. Whenever this instruction get decoded and executed, PC will pointing to this 20A4 location. Okay, when program counter is shifting to 20A4 location, this value, suppose this is 3204. Okay, call is written. So 3205 and 3206, these three locations are used to store this call instruction. So PC content, that is 3207, this content has to be stored somewhere, that is, it is stored on the stack. So this 3207, earlier in case of jump we don't require this 3207 because we are shifting the execution from one sequence to another sequence. But in case of call, we have to come back to the main program. So that's why we need to store this 3207H, that is the content of PC. So before transfer from this location to a new location, that is subroutine, microprocessor has to store the content of program counter onto the stack. That is, it will done automatically by using push instruction. In case of this is the unconditional jump, unconditional call. This is unconditional call. It does not check for any condition to be satisfied. But we can have a conditional call also, that before calling some subroutine, microprocessor go and check for condition, whether this condition is true or false. Suppose I have written instruction CC3240. So this 3240 is the location where I have written the subroutine. But this subroutine is called by microprocessor in a main program only when carry flag is set. If carry flag is not set, then this instruction will not be executed and the main program is only be executed by microprocessor. Now, as I told you, in case of conditional call or unconditional call, we are calling a subroutine program, and at the end of that subroutine we must have to write RET. This RET instruction written, this instruction will give a command to microprocessor that now program counter has to be reloaded with the content that is pushed on the stack. So whenever this RET instruction is executed by microprocessor, nothing will be done. It will only get popped the content of program counter, means program counter will be reloaded with the previous location in the main program. So in case of unconditional call, we have to write RET, means if in main program if I have call some add program, then at my addition program I have write some instructions and at the last I have to write RET, that is unconditional return. In case of conditional return, means if I am using CC in my main program to call an subroutine, then that subroutine must be ended by RC or any other RNC, or depend on the programmer, but it has to be written with condition. Now the next branching instruction is RST, that is restart. There are some software interrupts and also there are some hardware interrupts. In case of 8085, we have 5 hardware interrupts, means we have 5 external pins available in 8085, which we can use to interrupt the execution of microprocessor 8085. But we also have in 8 software interrupts, that means whenever this instruction is executed, like RST1 or RST2 or RST5 or RST6, a particular set of program get executed. That particular set of instructions are related to that particular restart instruction, that is software interrupt. Like in main in our program, in our labs or in our simulator, we mostly use hardware simulator, we mostly use RST5. This RST5 is the end of that particular program. It instruct it indicates microprocessor that RST5 instruction will be used to stop that particular program where we have written this instruction RST5, and its address is 0028. Okay, for corresponding to RST0 we have address 000. So if we use in our main program, if we are using RST0 or in our subroutine we are using RST0, then the control will goes to the vector address 00h, that is the start of the main program. Now the last group, that is machine control group. These are the instructions which are used to control the operation of microprocessor. One of them is NOP. This instruction is nothing but, as name says, no operation. So no operation is to be performed, only fetch and decoded. No execution will be done. So this instruction is only used to insert a delay. If we have to insert a delay, that if we want that 2 instruction has to be executed with some delay, then in that case we introduce NOP between the execution of that 2 instruction. Then next machine control is HLT, that is halt. CPU finishes executing the current instruction and halt any further execution. So this is nothing but we can use to stop the execution of SCPU, that we can ask CPU to finish the program. So if we use halt at the end of our program or instructions, then this is the last instruction in our program and it will stop the execution of CPU. So in our kit we can't use this HLT signal, because if we use this HLT signal, then CPU will not perform a display function or keyboard function, it will stop the execution. So mostly we avoid to use halt signal, otherwise it stop our kit. EI, enable the interrupt. There are 5 hardware interrupts, and if we want to enable all the interrupts, we have to use this instruction. This instruction is used to enable all the interrupt. If we use DI, then we can disable the interrupt, means only trap, that is non-maskable interrupt, can be executed by microprocessor. Rest of the interrupts are not able to interrupt the main function. So if we have to perform some main task, and in that task we don't want an hardware circuitry to interrupt the microprocessor functioning, then in that case in our main program we can write first DI, we can give the task to microprocessor, and then if we want we can write EI to enable the interrupt when that task is completed. SIM. This instruction perform multiple operations, that it is used to implement this hardware interrupts RST 7.5, 6.5, 5.5, and also this instruction is used to serially transfer the data, serially out the data. So whenever the SIM instruction is executed, we use this instruction to transfer our data serially, and also we use the SIM instruction to set the interrupts, whether hardware interrupt, whether we have to mask the interrupt or we have to enable the interrupt. So how we are going to do that? If we write this instruction SIM, then before using this instruction we have to initialize accumulator, because whenever the SIM instruction is executed, the accumulator get whatever the content of accumulator, that can be used. For example, if I have to transfer some data serially, if I have to transfer 1, then I have to store at the D7th bit of accumulator. So if I have to transfer 1, I will store it at SOD, that is serial data out, and I use the instruction sim. This data will be out to the SOD line. Okay, and SOE, this line, enable serial data. So if this bit is 1, then only this data gets outputted, or you can say it is transferred on the serial line. If this bit is 0, then it will ignore this SOD. So we have to set here the data and here the enabling line. This is the don't care condition. X stand for don't care. Either we can use 0 or 1. RST 7.5. If I have to reset this interrupt, then I will use this pin, is this bit of a accumulator, and I will make it 0. If I have to mask any of these interrupts, there are 3 hardware interrupts: 7.5, 6.5, 5.5. Trap is the non-maskable interrupt, and there is INTR. But if I have to mask either of these, I can make it 1 for masking, I can make it 0 for unmask, and this is used for enabling the masking. If I make it 0, it will ignore whatever this masking is there, and if I have make this bit number 3 as 1, then we can use this masking. RIM. The next instruction, that is RIM. It is a read instruction. SIM is used to set the interrupt, whether we have to mask the interrupt or enable the interrupt or disable the interrupt. RIM is used to either read the status of the interrupt, what is the status of that particular interrupt, and also to read the serial data. Whenever the data is in from SID line, it will stored in accumulator. So the structure, again accumulator come into picture when we are using RIM instruction. This SID line is used for data input. P7, 6 bit, 5th bit and 4th bit. These bits are used for indicating the status of the interrupt. So if any of the interrupt is pending, then this bit will be 1. We are reading. So if any of the interrupt is in pending mode, that particular interrupt is represented by 1. If no request is pending, it is represented by 0. Value of the interrupt enable flip flop. What is the value of enable flip flop? Whether it is 1 or 0, it is represented at here. Masked and unmasked. This is the status when suppose there is one module, another module is written by some other programmer, and I have to check whether that particular programmer has masked any of the interrupt or unmasked any of the interrupt. So for checking the status of masking or unmasking of these 3 interrupts, I will use RIM's instruction. I will use in my program RIM, and I will check the status of these 3 interrupts. So these are some machine control operations, and we have discussed about all the instruction set of 8085. Thank you.